Hello guys, welcome to our 14th lecture on our course on photonic devices. On today's lecture we're going to talk about the joint density of states for transitions between the conduction and the valence bands, and also we're going to define the quasi-Fermi levels. So when we're dealing with semiconductors for optical applications, as for example optical sources and detectors, we are most interested in the transitions between the bands, right? So for example, in the case of absorption, an electron can gain energy that is supplied by the photon that is absorbed, and then transit from the valence band up to the conduction band. So it'll gain energy, and this energy will be supplied by the impinging photon, which after the absorption it no longer exists. On emission, on the other hand, the electron will lose energy and transit down from the conduction band into the valence band, and in this process it will release a photon with the energy that the electron has lost. Okay, and since we're interested in these transitions, it's important to know, the density of states in the valence band, so rho v of E, and in the conduction band rho c of E, in order to quantify the number of states available in the conduction and valence bands for a given energy. So, for example, we have seen that rho v of E, the density of states in the valence band, was defined in such a way that rho v of E dE is the number of states with energies in the interval between E and E plus dE per unit volume. For optical application, it's more convenient to quantify the density of allowed transitions, with emphasis on transitions here, between two distinct energy values, and this is done by the joint density of states. So the joint density of states is defined as the density of possible transitions rather than the density of levels of states itself. It's the density of transitions between two distinct energies, EI, the initial energy, and EF, the final energy. Okay, so to try to get a better grasp of what this density of states will be, we can think of the band diagram with the rho of E, the density of states, the regular density of states which we have seen, plotted alongside in the conduction band and in the valence band. So we saw that the density of states grew with the square root of E towards the center of the band. So as you went towards the center of the conduction band, there are more energy levels, and as you went to the center, away from the edge of the valence band, there are more energy levels. The density of states gets larger. Well, now if we're interested in the transitions, we are actually interested in a pair of energy levels, right? Usually one in either the conduction band or the valence band. So you might have, if you're considering the process of emission, you might have an initial level EI in the conduction band and a final level EF in the valence band. And when the electron transitions down from the conduction band into the valence band, so from EI to EF, it emits a photon. So we're interested in the transition between pairs of states, right? One in the conduction band and another one in the valence band. And it's important for us to know the density of pairs of states associated with a given frequency. So if the electron transitions down from this level to this level, it will emit a photon with energy h times f, and therefore this difference in energy will correspond to a singular frequency here of the emitted photon. And now on the other hand, if we consider two different a different pair of energy levels, so let's say that EI was up here and EF was down here, then the transition would be from here to here. And we can clearly see that there are more states available up here as compared to the original EI, which is in green here, and there are more states down here than there are in the original EF, which was up here in the valence band. So therefore we would expect that the density of transitions is higher for this yellow transition here as compared to the green transition here, simply because, you know, there are less states close to the band edge in the valence band and also in the conduction band, and therefore there will be a higher number of states, both initial and final, so a higher density of pairs of states, and the joint density of states deals with this, right, with pairs of states and transitions. So the coupled density of states of pairs of states in the conduction and valence band. Okay, so this is more or less what the joint density of states represents. So it is rather than being associated with a single state in the conduction band, for example, it's associated with pairs of states in the conduction and valence band. So it's a density of states associated with pairs of states. Okay, but we'll define it more rigorously along this lecture. And we're interested in this because in order to calculate the emitted or absorbed power, for example, right, the power emitted by a laser or the power absorbed by a photodetector, we need to find the number of transitions per second. Okay, and in order to find this number of transitions per second, we will need the joint density of states, as we'll see. And this is important because you know, if we know the number of transitions per second, we know the number of photons emitted, and we also know the energy of each photon, so which is h times f. So if we multiply the number of photons emitted, which is the number of, you know, it will be related to the number of transitions, by the energy of a single photon, we can know the total energy emitted and the total power and so on. The number of transitions per unit volume is actually the product of two terms, right? The first one being the density of pairs of states available for transitions with energy corresponding to h, the Planck's constant, times f. And the second term is the probability of occupation of these two states, of the pair of states, right? In the first term, the density of pairs of states corresponding to an energy hf is the joint density of states. The second term here, the probability of occupation of these states, is important because, well, you can have lots of states. For example, in the process of emission, you might have a lot of states for electrons to occupy in the conduction band, and a lot of empty states that can be empty and therefore be associated with holes in the valence band. But if the probability that there are electrons in the states in the conduction band and that there are holes in the states in the valence band are low, there will not be many downward transitions, and therefore there will not be many emissions of photons, right? So aside from having, you know, large density of states both in the conduction and valence band, if you want to have many emissions, you need that the states in the conduction band be occupied by electrons and the states in the valence band be occupied by holes, because when the electron that's in the conduction band loses energy and transits down into the valence band and occupies the place of a hole, in this process it will emit a photon. Now, if there are a lot of empty states up in the conduction band and, you know, filled states in the valence band, there will not be a lot of emissions. So you need to have the probability of occupations, a large probability of occupation of electrons in the conduction band and holes in the valence band associated with the pairs of states that you're interested in. Okay, so the probability of occupation will also play a role, but the density of states, the joint density of states, needs also to be taken into account. So in order to derive the expression for the joint density of states, let us consider an emission process with a transition of an electron from an energy level EI in the conduction band to an energy level EF, or a final energy level, in the valence band. As we have seen, we can use the parabolic approximation for both these bands. So the energies in the conduction band can be described by this parabola equation right here, where you have the energy equal to the band edge energy EC, which would be this energy right here, right? Plus h bar squared over 2 times the effective mass of the electron, and all of this times k squared, so the magnitude of the wave vector squared. And the same thing goes for the valence band. With the parabolic approximation, you have the levels, the energies in the valence band described by EV, the band edge for the valence band, minus this constant h bar squared divided by 2 times the effective mass of holes, multiplied by k squared, right? And since the initial level is in the conduction band, this would be, using the parabolic approximation, how you could write the initial energy level and the final energy level in the valence band. And the energy of the photon is h times f, which is has to be equal to the initial energy minus the final energy level, so EI minus EF. So what I'm saying here is that the photon energy HF has to be equal EI minus EF, and we just have to subtract the last equation here from the first one. By doing this, we get EC minus EV. So EC minus EV, which is the gap energy, right? EC minus EV is exactly the forbidden gap energy. So this is EG, and if we proceed subtracting, you have this term right here minus this one, which is equal to this term plus this one. Okay, so what we end up having is plus h bar squared multiplied by k squared over 2 times, which is the common term to both of these, and this times 1 over mc star plus 1 over mv star. Okay, where mc is the effective mass of the electron and m in the conduction band, and mv is the effective mass of hole in the valence band, of holes in the valence band. And you know, this right here can be written in this form right here, right? If we multiply and divide the first term by mv star, then we get this mc star times mv star in the denominator, and up here we'll end up with mv star plus mc star. Okay, therefore, you know, we can write that hf is equal to eg plus h bar squared times k squared over 2 multiplied by this term here. So mv star plus mc star divided by mv star times mc star, which is what we have right here, right, where eg is the gap energy, which is equal to ec minus ev. Okay, so this is equation number 3, and in this equation we can now proceed to isolate this k squared term right here. So if we want to do this, we can pass this Eg to the other side, subtracting, so we'll have hf minus Eg, right, is equal to h bar squared times me star plus mh star divided by 2me star mh star times k squared. And then we just pass this term to the other side, dividing, and we get this right here. So k squared is equal to 2 divided by h bar squared multiplied by this term right here, so me star times mh star divided by me star plus mh star multiplied by hf minus eg. Okay, so this is expression number 4, and this gives us k squared. We can now go on to substitute this k squared in equation number 1. Okay, so we can replace it right here and get an expression for ei in terms of the frequency f, and we'll see in a minute why we're doing this. But again, if we substitute k squared here, we'll have all of this, you know, so 2 over h bar squared times me star times mh star divided by me star plus mh star multiplied by hf minus eg. So some things will cancel out. Basically this h bar squared will cancel with this one, the 2 will cancel with the 2 here, and this mc star, which is actually the mass of the electron in the conduction band, can cancel out this guy right here. Okay, and we end up with ei is equal to ec plus mh star divided by me star plus mh star multiplied by this term right here. So finally we end up here, and we have exactly what we said. ei is equal to ec plus mh star divided by me star plus mh star multiplied by hf minus eg. And this gives us the initial energy ei as a function of the frequency f. Notice that all of these other things are constant. So ec, you know, is the band edge for the conduction band. You have the effective masses here, the Planck's constant, and the gap energy, which is fixed for a given semiconductor. So note that there is a one-to-one correspondence between ei and f in this expression. So if this is actually equal to ei and all of these are constants, ec, you know, the effective masses, Planck's constant, then this is the equation for a line, which we can plot right here. So if we plot ei as a function of frequency f, we get a straight line, right? Because this is the expression for a straight line if we're looking at ei as a function of frequency f. And well, we know some points in this line, right? For example, for ei equal to ec, if we substitute ec here, then, you know, this term right here has to be equal to 0 because ei is equal to ec. And for this to be 0, we have to have eg equal to hf. Okay, so hf has to be equal to eg. Therefore, this will correspond to a point with frequency f equals to eg over h. And this is actually the point where the line stops right here, right at the leftmost end here. So we have ec equals to eg over h. right? This would be for the conduction band, right at the band edge. So for energies lower than this, you would be inside the band gap. It would correspond to frequencies corresponding to energies that were smaller than the band gap. So there could not be emission with frequencies lower than this point right here. But another important point here is that, we know that the energy levels are discrete. So in this line you would have discrete levels. So if there's a one-to-one correspondence, these discrete energy levels would correspond to discrete frequencies here. So we would have discrete frequencies, of course, and therefore, we can define the joint density of states rho of f in such a way that rho of f df is the number of allowed transitions for photon interactions with energies between hf and hf plus df. Okay, so in this graph here, if we have f corresponding to this point here and f plus a differential f, this point right here, then rho of f df would be the all of the states in this interval, so between hf and hf plus df. Okay, and since there's a one-to-one correspondence, we can write that rho of f df has to be equal to rho of e de, where e is the initial energy that we are considering, right? Because these states, in this interval are the same. The states between ei and ei plus dei are the same states between f and f plus df. There's a one-to-one correspondence. You'll have the same number of states, so we can write this equality right here, and we're doing this so that we can find an expression for the joint density of states rho of f. So if we isolate this and rewrite this expression, we can say that rho of f is equal to rho c of ei times dei df, the derivative of ei with respect to f. Well, we have the density of states in the conduction band, and we have found an expression exactly for ei as a function of frequency, which we can take the derivative of and get this term here as well. So we basically have everything so that we can get an expression for the joint density of states. So in our previous classes we have found the expression for the density of states both in the conduction and valence band. So in the conduction band, this is the expression for rho c as a function of E, right? And it goes with the square root of E, and if we want the expression for rho c as a function of EI, we just substitute E by EI here, right? The initial energy is an energy as well. So we have this, which is this guy right here. We have the expression. Now we need dei df. So again, we can just take the derivative of this. So if we take the derivative of this guy here with respect to f and ignore this part right here, the derivative of a constant EC will be equal to 0, and again, you have this constant times EG, which is also a constant here, so this will be 0 when we take the derivative with respect to f, and all that will remain is the derivative of this term right here. The derivative of f with respect to f is 1, so we'll end up with mh star times h divided by me star plus mh star. Okay, so we just take the derivative of this and we end up with this right here, right? The dei df is equal to mh star divided by me star plus mh star times h. And now sometimes I've been using mh or mv, but for the same thing, which is the effective mass of holes in the valence band, and also me star or mc star for the effective mass of electrons in the conduction band. Okay, so these are the same. And now if we take this guy right here, so expression number 8, and this guy right here, and we plug in here, so they're multiplying each other, we get rho of f. So rho of f ends up being, you know, this guy times this guy. So is what we got right here. And note that all of these are constants. Okay, these things, all of these terms inside the parentheses, as well as this, and these terms right here as well. So these and these are all constants. Now we want an expression for rho as a function of f. There's still one last thing that we need to do, which is to replace the variable here, which is ei, the independent variable ei, by f, and we have just the means to do this, because we have found an expression for ei as a function of f, which is expression number 5 again. Okay, so we know that ei is equal to this. Now what we have in the expression for the joint densities of states is actually the square root of ei minus ec. So we can, you know, take this equality and write that ei minus ec, so I'll just pass ec over to the left side, so ei minus ec is equal to mh star divided by me star plus mh star multiplied by hf minus eg, right? And well, we want the square root of this guy right here, so this goes into that equation, so we just take the square root, so we'll have the square root of this term right here and the square root of this term right here as well. Okay, so we can now just take this, you know, and plug in here, plug that in right here, and we get, you know, this is what I just did. Then we get, after some manipulation which you can check later, we finally get the expression for the joint density of states as a function of f. So rho of f is equal to all of these constants right here, which we get by substituting this here and doing a little bit of algebraic manipulation. And so this constant here times the square root of hf minus eg. So the joint density of states grows with the square root of frequency. So let's recall that by definition, this which we have just found is the joint density of states, which is defined in such a way that rho of f df is the number of pairs of states for photons with frequencies between f and f plus df to interact with. So basically, you know, if we draw the band structure for direct band gap semiconductor, for example, and we draw the conduction and the valence band close to the edge regions right here, again we'll have discrete energy levels both in the conduction and valence band, and we are interested now in transitions between, you know, an initial state which might be in the conduction band in the case of emission, of course, and a final state in the valence band in the case of emission, or final state. If we're talking about absorption, these would trade places, but we're looking at pairs of states, you know, for photons to interact with, which means that, you know, in the case of emission, you have electrons transitioning from the initial state into the final state with light emission. So this is the photon interaction right here, and the density, the joint density of states, gives us just this density, the density of pairs of states associated with a given frequency, which can be used for photon interactions.